Right now, as you listen to these words, you are hurtling through space at 515,000 miles per hour. You do not feel it. You cannot sense it. But the planet beneath you, the star it orbits, and every object you have ever touched is spinning around the center of a galaxy so large that light itself needs 100,000 years to cross it. And that galaxy, your galaxy, the only home your species has ever known, is not alone. It's 2.5 million light years away, separated by a void so empty that a single atom drifts alone through every cubic centimeter. Something waits. A structure containing 1 trillion stars. A disk of burning sun stretched across 220,000 light years of darkness. A giant that makes your entire galaxy look like its smaller sibling. The light reaching your eyes from its body tonight left before the first human ever walked upright. And it is falling toward you, not drifting, falling, pulled by gravity at 250,000 miles per hour every second for billions of years already. What happens when it arrives will reshape everything, but the collision is not the terrifying part. The terrifying part is what the distance between here and there reveals about where you actually stand in this universe. If this channel has ever shifted your perspective, consider subscribing. It costs nothing but means everything. What follows will dismantle every intuition you hold about size, distance, and existence itself. Once it begins, there is no going back. Prepare for a journey through the true architecture of cosmic distance. We begin. Close your eyes for a moment and picture the Earth from space. That famous blue marble hanging in darkness. Swirls of white cloud wrapped around blue ocean and brown land. You have seen this image 100 times. On posters, on screens, in documentaries that made you feel small for a brief moment, before you returned to your coffee and forgot about it. But you have never truly understood how big that marble is. Not really. Not in the way your bones would understand it if you tried to walk across its face without stopping. Let us begin where your feet touch the ground. The circumference of the Earth, the full distance around its widest belt at the equator, measures approximately 24,900 miles. That is a confirmed measured number. Satellites have verified it. Surveys have cross-checked it. It is as solid as any number in science. But solid numbers, and numbers your body can feel, are two very different things. So, let us make it physical. Imagine climbing aboard a commercial airplane, the kind you have probably sat inside, eating small bags of peanuts and watching clouds drift past your oval window. That airplane cruises at roughly 550 miles per hour. Now imagine it never lands, no fuel stops, no circling above a congested airport, no turbulence detours, just a straight, continuous, unbroken flight along the equator. At that speed, you would need just over 45 hours to return to where you started. Nearly 2 full days in the air, without rest, without pause, just to trace a single circle around the planet you were born on. Now take away the airplane and put yourself in a car, a comfortable one, up moving at 70 miles per hour on a perfectly straight highway that somehow wraps all the way around the equator without interruption. No traffic lights, no rest stops, no sleep, just driving. That journey would consume roughly 14.5 days, 2 entire weeks of continuous motion to outline the edge of one planet. This is Earth at human speed, and at human speed, Earth is enormous. But here is the thing your body does not want you to know. Your sense of what counts as big was never designed for planetary distances. It was designed for something much, much smaller. For most of the time our species has existed, we moved at roughly 3 miles per hour. That is walking speed. The pace your legs naturally settle into when you cross a field or follow a riverbank. For hundreds of thousands of years, that was the fastest most humans ever traveled. Our brains learned to judge distance based on that speed. A nearby hill meant a short walk. A distant mountain meant a long one. A river too wide to cross meant danger. That was the full range of our spatial awareness. River crossings, seasonal migrations, the distance between a sleeping place and a watering hole. The entire navigation system inside your skull was built for a world measured in footsteps, not in thousands of miles. And yet, even at walking speed, our ancestors eventually covered astonishing ground. When early humans walked out of Africa roughly 70,000 years ago, they did not know they were beginning a migration that would span continents. They were simply moving, following food, following water, following seasons. Generation after generation, families drifted a little farther from where their grandparents had lived. Children were born in places their great-grandparents had never seen. That slow, generational drift eventually carried human beings all the way to the southern tip of South America, and it took approximately 10,000 years to get there. 10,000 years of gradual, multi-generational walking to cross what was, from the planet's perspective, only a fraction of its surface. Think about that for a moment. 10 millennia of continuous human migration, the greatest journey our species ever made on foot, and it covered only a portion of a single world. Earth was so much larger than the bodies that evolved on it, that crossing even part of its face required a span of time, longer than all of recorded history. This is the planet you think you know. You have flown over it. You have watched it rotate on screens. You have seen its entire face in a single photograph taken from the moon. And because you have seen it whole, your brain tells you it has been conquered, measured, understood, made small by technology and perspective. But your brain is lying to you. Earth's diameter stretches roughly 7,918 miles from one side to the other. That is the distance straight through the planet's core, from the ground beneath your feet to the point on the opposite side of the world, directly below someone else's feet. Almost 8,000 miles of rock, magma, liquid iron, and compressed matter so hot and dense that no drill, no probe, no instrument has ever come close to reaching the center. The deepest hole humanity has ever bored into the Earth is the Kola Superdeep borehole in Russia. After 20 years of drilling, engineers reached a depth of approximately 7.5 miles. That sounds impressive, until you realize it represents less than 0.1% of the distance to Earth's core. We scratched the skin of the planet and called it an achievement. The planet did not notice. And here is something strange that most people never consider. We have better maps of the surface of Mars than we do of our own ocean floor. More than 80% of Earth's ocean remains unmapped and unexplored. We live on a world we have not finished looking at, a world with trenches and ridges and underwater mountain ranges that no human eye has ever seen directly. There are creatures swimming in the deep ocean right now that science has not yet named. There are geological formations beneath the waves that would dwarf anything on land, and we do not even know their shapes yet. Some scientists have even speculated that deep beneath the ocean floor, in pockets of heated rock and mineral-rich water, microbial ecosystems may exist that are entirely independent of the sun. Life that has never seen light, life that draws its energy from the chemistry of the Earth itself, existing in total isolation from everything we think of as the living world. If true, the biosphere of this planet extends deeper and stranger than any textbook currently describes. that remains an open and active area of scientific investigation, one that reminds us how much remains hidden even on the world we call home. This is the first and gentlest truth of this journey. The planet you stand on is genuinely, physically, measurably immense by every standard your body was built to process. It took our species 10,000 years to walk across part of it. It would take 2 weeks of non-stop driving to circle it. Its interior remains largely unreachable. Its oceans remain largely unseen. You live on a world that still holds secrets from the species that named it, mapped it, and believed it had been fully understood. And none of this matters, because everything you just felt, that sense of planetary enormity, that quiet awe at the size of the world beneath your feet, is about to be taken from you, gently, permanently, one level at a time. The Earth is about to start shrinking, and once it begins, it will never stop. That feeling of enormity you just built, that sense of a planet too wide to walk across, too deep to drill into, too vast to fully map even after centuries of exploration. Hold it in your mind for one more moment. Feel its weight. Appreciate its scale. Because what comes next will make it vanish like a candle flame pinched between 2 fingers. We are going to look at the deepest wound the Earth carries on its body. And then we are going to watch that wound disappear. In the Western Pacific Ocean, east of the Philippines and south of Japan, the ocean floor drops away into a darkness so absolute that the word dark does not do it justice. This is the Mariana Trench, and at its lowest point, a narrow slot called the Challenger Deep, the ocean plunges to approximately 36,000 feet beneath the surface. That is nearly 7 miles straight down. Let that distance settle into your body for a moment. 7 miles, directly beneath the waves, straight into black water that gets colder and heavier with every foot you descend. Within the first 1,000 feet, sunlight gives up. It simply cannot push any deeper. Below that line, the ocean exists in permanent, total, unbroken night. No dawn has ever reached those depths. No sunset has ever painted those waters. There is only pressure and cold, and a silence so complete that the concept of sound begins to lose its meaning. And the pressure is the thing that makes this place a genuine frontier of survival. At the bottom of the Challenger Deep, the water pushes against everything with a force exceeding 16,000 pounds per square inch. That is roughly 1,000 times the air pressure you feel right now sitting wherever you are. Imagine taking every step you have ever walked, every object you have ever lifted, every weight you have ever felt pressing against your body, and multiplying that sensation by 1,000. Then imagine it pressing equally from every direction at once. That is what waits at the bottom of the ocean. Fewer than 30 human beings in all of history have ever reached that depth. Each one traveled inside a custom-built submersible with walls made of titanium and specially engineered alloys designed to resist forces that would collapse a military submarine like a crushed soda can. These were not casual dives. They were missions planned over years, backed by teams of engineers, and executed with the understanding that a single structural failure at depth meant instant death with no possibility of rescue. When filmmaker James Cameron made his solo descent to the Challenger Deep in 2012 inside the Deep-Sea Challenger submersible, the vehicle's hull was subjected to pressures so extreme that it physically compressed during the dive. The entire craft shrank by roughly 3 inches under the weight of the water above it. Cameron descended for 2 hours and 36 minutes into absolute darkness, reached a world no sunlight had ever touched, spent a brief time at the bottom, and returned. The entire experience felt like visiting another planet. And here is something genuinely strange that scientists are still trying to fully understand. At those crushing depths, in that freezing darkness, life exists, not just microbial life, though that is abundant. Actual visible creatures move through the blackness of the deepest trenches. In 2014, a species of snailfish was filmed swimming calmly at a depth of over 26,000 feet in the Mariana Trench. It looked pale, translucent, almost ghostly, drifting through pressures that would destroy nearly any machine humans have ever built. How these organisms maintain cellular integrity under such forces remains an active area of biological research. Their proteins, their cell membranes, their entire biochemistry operates under conditions that should, by our surface world understanding of biology, make complex life impossible. Yet there they are, swimming, feeding, reproducing, thriving in a place that would kill you in a fraction of a second. Some researchers have even suggested, and this remains speculative and debated, that the deep ocean trenches of Earth might serve as useful models for thinking about potential life beneath the ice-covered oceans, of moons like Europa and Enceladus. If biology can solve the problem of extreme pressure and total darkness here on Earth, perhaps it has solved similar problems elsewhere in the solar system. In oceans we have not yet touched, beneath crusts of ice we have not yet broken through. But now comes the part that quietly breaks something inside your understanding of scale. You just felt the Mariana Trench. You felt its depth, its pressure, its darkness. The decades of engineering required to reach its floor. The handful of humans brave or stubborn enough to descend. It felt like one of the most extreme places on this planet. And it is. By every human standard, the Challenger Deep represents a genuine boundary of exploration, a place that fights back against every attempt to reach it. Now zoom out, just one level. Not to the stars, not to the solar system, just to the planet itself, seen whole. Earth's diameter is roughly 7,918 miles. The Mariana Trench, the single deepest scar on this planet's entire surface, digs less than 7 miles into a sphere nearly 8,000 miles across. Do the math. That trench represents less than 0.1% of the distance through the Earth. It is not a wound. It is not even a scratch. It is a faint imperfection so shallow that it barely registers against the full body of the planet. Here is how to feel this instead of just reading it. Take a standard basketball. Hold it in your hands. Run your fingers slowly across its surface. Feel the texture, the tiny bumps of the pebbled leather or rubber. Now understand this. If you shrank the Earth down to the size of that basketball, the Mariana Trench would not be something your fingertip could detect. It would be smaller than the tiniest bump on the ball's surface. You could search the entire sphere with your most sensitive touch, and the deepest point in the ocean, the place that required custom titanium submersibles and years of engineering to reach, would feel like nothing. Smooth, flat, invisible. The feature that pushed human engineering to its absolute limit is, at planetary scale, a rounding error. It might as well not exist. And this is not just true for the Mariana Trench. Mount Everest, the tallest point on Earth's surface, rises approximately 5.5 miles above sea level. On that same basketball, Everest would be equally undetectable. The full vertical range of Earth's surface, from the deepest ocean trench to the tallest mountain peak, spans roughly 12.5 miles. On a planet 8,000 miles wide, that entire range, everything from the bottom of the sea to the top of the sky-piercing Himalayas, represents a surface variation so tiny that the Earth, if shrunk to a billiard ball, would actually be smoother than the billiard ball itself. This is a verified fact. The World Pool Billiard Association specifies surface tolerances for regulation billiard balls. Earth, scaled to that size, would fall within those tolerances. The planet you experience as a world of towering mountains and crushing ocean depths is, in geometric reality, smoother than the polished ball rolling across a pool table in a bar. Sit with that for a moment, because this is the first true lesson in what happens when you change your viewing distance by just one level. Things that feel immense become invisible. Features that challenge survival become undetectable. The most extreme environments your planet possesses dissolve into a smooth, featureless curve the moment you pull back far enough to see the whole. And this pattern, this quiet vanishing act where each scale erases the drama of the one before it, is going to follow us for the rest of this journey. Every time you think you have found something truly enormous, something that finally anchors your sense of scale, the next level up will take it away. We have not even left the surface yet, and already the deepest and highest points on Earth have been reduced to nothing. Now imagine what happens when we lift our gaze 93 million miles upward toward a light so bright it has been burning for 4.5 billion years without pause. That light you feel on your skin when you step outside on a clear morning. That warmth that makes you close your eyes and tilt your face upward without thinking. It is not what you believe it is. It is not gentle. It is not soft. It is not the quiet, friendly glow your body tells you it is. What touches your face each morning is the remnant of a violence so extreme that no language built on Earth can properly contain it. That warmth traveled 93 million miles of absolute emptiness to reach you. It crossed a vacuum where no sound exists, where no air moves, where temperature itself loses its meaning because there is nothing there to be hot or cold. And it did all of this in 8 minutes and 20 seconds. That number deserves your full attention. 8 minutes and 20 seconds. That is how long light needs to travel from the surface of the sun to the surface of your eye. Light, the fastest thing the universe permits. Nothing with mass can match it. Nothing with mass can even approach it. It moves at roughly 186,000 miles per second. Not per hour, per second. And even at that impossible velocity, the gap between you and your own star takes over 8 minutes to cross. Think about what this means in terms you can actually feel. If the sun vanished right now, this very instant, simply ceased to exist, you would not know for 8 minutes and 20 seconds. You would still see it in the sky. You would still feel its heat on your arms. You would keep living in complete ignorance of the most catastrophic event imaginable for roughly the time it takes to boil water and make a cup of tea. The sky would look normal. The world would feel normal. And then, 8 minutes later, the light would simply stop arriving. The sky would go dark. And only then would you understand that the source had been gone for longer than you realized. That is how far away we are from our own star. Not from some distant object at the edge of the galaxy. From the thing that rises every morning and sets every evening. The most familiar object in your sky sits 93 million miles away, a distance so vast that even the fastest phenomenon in existence needs a full 8 minutes to bridge it. Astronomers call this distance one astronomical unit, 1 AU. It sounds clinical, tidy, like a unit you might find on a ruler, but let us strip away the tidiness and feel the actual distance with a human body. If you boarded a commercial airplane and flew directly toward the sun at 550 miles per hour, never landing, never resting, and never circling, the flight would take over 19 years. A child born on the day you departed would be old enough to vote, to drive, to have finished school before you arrived. At the speed of a rifle bullet, roughly 1,700 miles per hour, you would still need more than 6 years. 6 years of traveling at bullet speed just to reach the nearest star. That is the emptiness between you and the sun. And across that emptiness, the object waiting at the other end is not what your morning experience suggests. The sun is not a warm lamp hanging at a comfortable distance. It is a sphere of superheated plasma, 864,000 miles across. To feel that size in terms your body can process, consider this. You could line up 109 Earths side by side, edge to edge, and they would just barely stretch from one side of the sun to the other. And 109 copies of the world that took your ancestors 10,000 years to walk partway across, placed in a row, and they would only just match the width of your star. But width is the gentle comparison. Volume is where the numbers become violent. Approximately 1.3 million Earths could fit inside the sun. Not beside it, not near it, inside it. Every continent, every ocean, every city, every mountain range, every war, and every love, every footprint ever pressed into the soil of this planet, replicated 1.3 million times, and the sun would swallow every single copy with room left over. The object you glance at casually through your car window each morning is a thermonuclear furnace so massive that the Earth is by comparison a grain of sand sitting at the mouth of a blast furnace. And it dominates everything nearby in a way that goes beyond size. The sun contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every speck of dust drifting between the orbits makes up the remaining 0.14%. Jupiter, the largest planet in our system, a gas giant so enormous it could swallow more than 1,300 Earths inside its volume, is a gravitational footnote next to the Sun, while Earth does not even register as a footnote. It is a cosmic crumb orbiting a nuclear engine that converts roughly 4 million tons of its own mass into pure energy every single second. Let that settle. 4 million tons per second. Not per year, not per century. Every tick of the clock, the sun annihilates matter equivalent to roughly 22,000 fully grown blue whales. He's converting their mass entirely into electromagnetic radiation and neutrinos that stream outward in every direction at the speed of light. And it has been doing this continuously for approximately 4.5 billion years. It will continue for roughly another 5 billion before its hydrogen fuel runs out and it begins to swell into a red giant, eventually shedding its outer layers and collapsing into a white dwarf remnant no larger than the Earth. Here is something most people never hear about, and it borders on the strange. Deep inside the sun's core, where fusion occurs, individual photons of light do not travel straight outward. They are absorbed and re-emitted by the dense plasma surrounding them, bouncing randomly in every direction like a person trying to push through an impossibly thick crowd. This process is so slow, so tangled, that a single photon generated at the sun's core can take anywhere between 10,000 and 170,000 years to reach the surface. The light warming your face this morning may have been born inside the sun before the last ice age ended on Earth. It spent millennia fighting its way outward through the sun's body, and then crossed 93 million miles of empty space in just 8 minutes. The last leg of its journey was the easiest part by far. And here is something that scientists are still working to fully understand. The sun's corona, the outermost layer of its atmosphere, is far hotter than the surface below it. The surface burns at roughly 10,000 degrees Fahrenheit. The corona, the wispy, ghostly halo you can see during a total solar eclipse, reaches temperatures exceeding 2 million degrees. That is counterintuitive in a way that still puzzles physicists. It is like walking away from a campfire and finding that the air 10 feet from the flames is hundreds of times hotter than the flames themselves. Several competing theories attempt to explain this coronal heating problem involving magnetic field dynamics, wave dissipation, and nanoflares too small to observe individually. But a definitive consensus answer remains elusive. The Sun has been studied more intensely than any other star in the universe, and we still do not fully understand why its outer atmosphere is hotter than its surface. Despite all this fury, all this scale, all this energy output that would vaporize any object that approached too closely, our Sun is profoundly ordinary. It is classified as a G-type main sequence star. Not particularly bright, not particularly massive, not particularly old. In a galaxy containing 400 billion stars, our Sun ranks among the most common category. It is an average star in an average location doing average star things. And yet, its scale makes every structure humanity has ever built, every distance humanity has ever traveled, every measurement humanity has ever celebrated, feel like a child's drawing taped to the wall of a cathedral that stretches beyond sight. You have now measured the Earth against your body and watched the planet shrink. You have measured the Earth against itself and watched its deepest scars vanish. And now you have measured the Earth against its own star and watched the entire planet dissolve into a speck barely worth mentioning. But the Sun is only the center of a much larger emptiness, and that emptiness stretches outward for billions of miles in every direction, filled with almost nothing at all. The Sun holds everything. That is the truth we just uncovered. A single object containing nearly all the mass in our solar system, burning with a fury that makes the Earth look like a speck of cooled ash drifting near a furnace. But now we need to understand what fills the space around that furnace. And the answer, the honest, uncomfortable answer, is almost nothing. You have probably seen diagrams of the solar system in textbooks or on classroom walls. The Sun in the center, then Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all arranged in neat little circles, evenly spaced, close enough that you can see all of them on a single page. Those diagrams are useful for learning the order of the planets, but they are lying to you about something fundamental. They are lying about the emptiness. The real solar system is not a tidy arrangement of nearby worlds. It is a vast, featureless ocean of vacuum with a few tiny objects scattered so far apart that finding them requires mathematics, not eyesight. Let us walk outward from the Sun and feel the distances grow. Earth sits 93 million miles from the Sun. Mars orbits farther out at approximately 142 million miles. That gap between Earth and Mars, roughly 50 million miles at the closest approach, it is already so enormous that a radio signal traveling at the speed of light needs between 3 and 22 minutes to cross it, depending on where both planets sit in their orbits. When NASA engineers send a command to a rover on Mars, they type the instruction, press send, and then wait. There is no instant response, no real-time conversation, just silence, followed by a gap measured in minutes, followed eventually by a faint confirmation that the signal arrived. But Mars is practically next door compared to what lies beyond. Jupiter, the first of the gas giants, circles the Sun at roughly 484 million miles. Saturn drifts at 886 million miles. Uranus floats at approximately 1.8 billion miles. And Neptune, the outermost recognized major planet, he orbits at a staggering 2.8 billion miles from the Sun. That outermost orbit means something specific for anyone trying to communicate across it. A beam of light leaving the Sun takes over 4 hours to reach Neptune. a radio signal sent from mission control on Earth to a spacecraft operating near Neptune, traveling at the absolute fastest speed the universe allows, requires approximately 4 hours to arrive. If that spacecraft encountered an emergency and radioed home for help, the operators in Houston would not hear the distress call for 4 hours. Their reply would take another 4 hours to travel back. 8 hours of round-trip delay at the maximum speed physics permits. For all practical purposes, a spacecraft near Neptune operates alone. It makes its own decisions, or it follows instructions uploaded hours in advance. There is no joystick on Earth controlling it in real time. There is no human hand guiding it through a crisis. There is only the machine, the void, and an 8-hour silence between question and answer. This isolation is not theoretical. It has been experienced by every deep space mission humanity has ever flown. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, the closest approach happened entirely on autopilot. Mission controllers had uploaded every command hours before the flyby began. The one-way signal time from Earth to Pluto exceeded 4.5 hours. There was no possibility of real-time guidance, no possibility of saying turn left or take that photograph now. The spacecraft executed its observations alone, stored the data on board, and then spent more than 15 months slowly transmitting the results back to Earth at a speed of roughly 1 to 2 kilobits per second. The entire scientific harvest from a flyby that lasted hours took over a year to download, 1 year to send photographs across the solar system, and Pluto is close compared to where our farthest traveler has gone. Voyager 1 was launched on September 5th, 1977. After nearly 5 decades of continuous flight at approximately 38,000 miles per hour, it has traveled roughly 15 billion miles from the Sun. It communicates with Earth using a radio transmitter that operates at roughly 22 watts. 22 watts. That is about the power of a refrigerator light bulb. The kind of dim glow you see when you open the door at midnight looking for leftovers. At that tiny signal spreads outward in all directions as it crosses the solar system, growing weaker with every mile. By the time it reaches NASA's Deep Space Network antennas on Earth, the received power measures roughly 0.1 trillionths of a watt. That is approximately 10 billion times weaker than the power needed to run a standard digital wristwatch. Engineers must use cryogenically cooled receivers and hours of careful signal, averaging just to pull intelligible data from the background noise of the universe. Think about that image. A machine the size of a small car, built in the 1970s, drifting through absolute darkness 15 billion miles from home, whispering back to Earth with the energy of a refrigerator bulb. And on Earth, a team of engineers pressing the most sensitive listening equipment ever built against the sky, straining to hear a voice so faint it barely exists above the static. That is what communication looks like at the edge of our solar system, not the crisp, instant data transfers you experience on your phone. Not the clean video calls or streaming signals that feel effortless in daily life. Out there, communication is a thin, fragile thread stretched across billions of miles of emptiness, fraying a little more with every mile it spans. Here is something most people find surprising. Despite traveling for nearly half a century, despite covering 15 billion miles, Voyager 1 has not left the solar system. Not by the most complete definition. It crossed the heliopause in 2012, the boundary where the solar wind gives way to the interstellar medium, making it the first human-made object to enter interstellar space by that specific measure. But the Sun's gravitational influence extends enormously beyond that boundary. The Oort cloud, a hypothesized spherical shell of icy bodies surrounding our solar system, is estimated to reach as far as 100,000 astronomical units from the Sun. That translates to approximately 1.6 light-years. The full gravitational territory of our single, unremarkable, middle-aged star may stretch 2 to 3 light-years in diameter, and Voyager 1 has crossed a tiny fraction of that territory. It has left the porch, but not the property. Here is something stranger still, something that touches the edge of what we do not know. Some scientists have noted that both Voyager 1 and Voyager 2 experienced a slight but unexplained deceleration during parts of their journeys that did not perfectly match predictions based on known gravitational forces. This became known as the Pioneer anomaly, first observed with the Pioneer 10 and 11 spacecraft and later investigated in the context of the Voyager missions. The most widely accepted explanation attributes the anomaly to thermal radiation pressure, a tiny push caused by heat radiating unevenly from the spacecraft's own electronics. But for years before that explanation was confirmed for the Pioneer craft, the anomaly sparked genuine scientific debate about whether our understanding of gravity at very large distances might be incomplete. Some physicists proposed modifications to gravitational theory to account for it. The debate is largely settled for the Pioneer case, but the broader question it raised, whether gravity behaves exactly as expected across truly vast distances within our own solar system, remains a question that future deep space missions may help refine. And this brings us to the real character of the solar system, the truth that no classroom diagram ever shows you. The defining feature of this place is not the planets, it is not the moons, it is not the asteroid belt or the icy fragments drifting beyond Neptune. The defining physical reality of our solar system is the absolutely staggering volume of empty space between everything. Space that contains functionally nothing. No air, no sound, no resistance, no landmarks. Just vacuum stretching in every direction for billions upon billions of miles, punctuated by occasional lumps of rock, gas, nor ice so small relative to the gaps between them that locating them requires precise mathematical coordinates rather than any form of looking. Your solar system is not a neighborhood. It is an ocean with a handful of pebbles scattered across it, each one so distant from the next that the ocean itself becomes the only thing that truly exists in any meaningful quantity. And we have not even tried to measure the distance to the nearest star beyond our sun. That distance makes everything inside the solar system feel like a single front porch step. And what waits beyond that step is a desert so wide it would swallow Voyager whole without noticing. You just felt the emptiness inside our solar system. Billions of miles of vacuum between scattered worlds. A spacecraft whispering with the power of a refrigerator bulb across 15 billion miles of darkness. Communication delays measured in hours at the speed of light. An ocean of nothing with a few tiny pebbles floating in it. Now, we step beyond the porch, and the desert that waits outside makes everything we just measured feel like the width of a doorway. The nearest star to our sun is called Proxima Centauri. It sits approximately 4.25 light-years away. That sounds like a small number. 4. Just 4. You can count to 4 on one hand, but that small number is a disguise wrapped around a distance so extreme that it breaks every comparison we have used so far. 1 light-year equals approximately 5.88 trillion miles. Not billion. Trillion. So a 5 followed by 12 zeros. Now multiply that by 4.25. The distance to the nearest star, the closest sun beyond our own, measures roughly 25 trillion miles. 25 trillion miles of nothing. Let us try to make that distance physical using a scale model we started building earlier. Imagine shrinking the sun down to the size of a large grapefruit, roughly 8 inches across. At that scale, Earth becomes a tiny pebble sitting about 75 feet away. Neptune, the outermost major planet, floats nearly half a mile from that grapefruit. The entire solar system, every planet, every moon, every asteroid, every comet, fits inside a modest small town. Now, at that same scale, where the sun fits in your palm, Proxima Centauri would be another grapefruit sitting approximately 4,000 miles away. Imagine standing at your front door in New York City holding your grapefruit sun. The nearest neighboring star would be another grapefruit resting somewhere in the middle of the Pacific Ocean, roughly halfway to Japan. 4,000 miles of empty, featureless terrain between one star and the next, closest one. That is the gap between suns in our region of the galaxy. Not the gap between planets. Not the gap between moons. The gap between entire star systems. And that gap is filled with a void so sparse, so hostile, and so featureless that crossing it represents a challenge fundamentally different from anything inside the solar system. The space between stars is called the interstellar medium, and while it is not perfectly empty, calling it full of anything would be generous to the point of dishonesty. On average, in our region of the Milky Way, the interstellar medium contains roughly 1 atom per cubic centimeter, like one single atom floating alone in a space the size of a sugar cube. Compare that to the air you are breathing right now. Every cubic centimeter of air in your living room contains approximately 25 billion molecules. The difference in density between the air in your lungs and the space between stars spans a factor so enormous that the interstellar medium qualifies as a better vacuum than anything we have ever manufactured in a laboratory on Earth. Our most advanced vacuum chambers still contain millions of molecules per cubic centimeter. The space between stars is emptier than anything human engineering can create. But that emptiness is not passive. It is not a harmless blank space waiting to be crossed like an open field on a calm day. The interstellar medium contains hazards that grow more dangerous the faster you try to move through them. Stray hydrogen atoms drift through this space. Helium atoms float alongside them. Microscopic dust grains, each one smaller than a grain of pollen, hang suspended in the void. And threaded through everything, a bath of high-energy cosmic ray particles accelerated to near light speed by distant supernova explosions race through the medium like invisible bullets fired from every direction. For a slow-moving spacecraft like Voyager 1, traveling at 38,000 miles per hour, this material poses no meaningful threat. The density is far too low to create drag or cause damage at such speeds. But for any spacecraft attempting to cross interstellar distances in a reasonable time frame, the math changes dramatically. At 10% of the speed of light, roughly 67 million miles per hour, each individual hydrogen atom encountered by the spacecraft would strike the hull with the energy of a particle accelerator collision. Over the course of a 4-light-year journey, trillions upon trillions of these impacts would deliver punishing doses of radiation to the spacecraft's surface, erode shielding materials, and potentially destroy sensitive instruments. The microscopic dust grains become even more dangerous. At 10% of light speed, each grain impact would carry the kinetic energy of a small explosive charge. A fleck of matter too small to see with your naked eye would hit with the force of a tiny bomb. The void between stars is not a peaceful emptiness. It is a thin, invisible gauntlet that punishes speed. The faster you try to cross it, the more violently it resists your passage. And here is the number that reveals the true scale of this desert. At Voyager, one's current speed of 38,000 miles per hour, traveling continuously without stopping, without slowing, without encountering any obstacle, it would require approximately 73,000 years to reach Proxima Centauri. And Voyager is not even heading in that direction. 73,000 years. That is roughly 9 times longer than all of recorded human civilization. Every empire that has risen and fallen, every language that has been born and died, every war fought and forgotten, every cathedral built and crumbled, in all of that history repeated 9 times over, and Voyager would still not have arrived at the nearest neighboring star. The fastest object our species has ever launched into space cannot reach the next sun over in any time frame relevant to the survival of nations, languages, cultures, or possibly even species. Here is something that adds a strange and haunting dimension to this isolation. In the space between our Sun and Proxima Centauri, there may be objects we have never seen. Some astronomers have proposed the existence of rogue planets, worlds not bound to any star, drifting freely through interstellar space in complete darkness. These would be planets ejected from their original star systems by gravitational interactions billions of years ago, now wandering alone through the void without sunlight, without seasons, without any warmth except whatever residual heat their cores still carry from their formation. As some estimates suggest, there could be billions of these rogue worlds drifting through our galaxy, possibly outnumbering the planets that orbit stars. If true, the space between stars is not as empty as it appears. It may be populated by a vast invisible census of dark, frozen worlds that we simply cannot see because they emit no light. Detecting them is extraordinarily difficult, and their existence in large numbers remains an open question in astrophysics, supported by some gravitational lensing observations, but far from conclusively established. The idea that our interstellar neighborhood might be littered with invisible frozen worlds, each one a potential graveyard of geological history, each one carrying the chemical ingredients that could have supported life under different circumstances, adds a layer of quiet strangeness to the void. The desert between stars may not be as barren as it looks. It may be full of dark, silent passengers we have not yet learned to count. But even if those rogue worlds exist in the billions, they do nothing to shorten the distance. They do nothing to ease the crossing. They sit in darkness, separated from each other by distances almost as vast as the gaps between the stars themselves. The interstellar desert remains what it is, a space so wide, so empty, and so hostile to speed that it transforms the simple concept of traveling from one sun to another into a problem that borders on impossibility for any technology we currently possess or can seriously envision building. And yet this desert, this 73,000-year crossing to reach a single neighboring star, is just the gap between two houses in a city of 400 billion houses. The city itself, the full structure that contains every one of those stars and every one of those interstellar deserts, stretches across a span of space so wide that even the distance to Proxima Centauri becomes just another vanishing speck. We are about to see that city from above, and nothing we have measured so far will survive the view. Every distance we have measured so far, every number that made your intuition flinch, every comparison that forced your brain to recalibrate what qualifies as large, describes a region of space so tiny within our galaxy that it is, for all practical purposes, invisible. The solar system with its billions of miles of emptiness, the 4 light-year desert to the nearest star, the 73,000-year journey that Voyager would need to cross it. All of that exists inside a structure so vast that those measurements dissolve into it the way a single grain of salt dissolves into the ocean. That structure is the Milky Way, and we are inside it right now. The Milky Way is a barred spiral galaxy. If you could somehow lift yourself above the galactic plane and look down, you would see a vast pinwheel of curved arms made of stars, gas, and dust, all spiraling outward from a dense central bar of older, reddish stars. The disk of visible stars measures approximately 100,000 light-years across. To cross it at the speed of light, the fastest speed the universe permits, would take 100,000 years. A beam of light leaving one edge of the Milky Way on the day you were born would not reach the opposite edge until roughly 100,000 years after every trace of human civilization had crumbled into dust and been forgotten by whatever comes after us. The disk is relatively thin compared to its width. In our region, the galactic disk measures roughly 2,000 light-years from top to bottom. That makes the Milky Way shaped more like a dinner plate than a ball. But even 2,000 light-years of thickness is an enormous vertical distance. Light needs 2 full millennia to travel from the top surface to the bottom in our neighborhood. When the Romans were building their first roads across Europe, a photon leaving the upper surface of the galactic disk near our position would only now be arriving at the lower surface. To 2,000 years of travel at the maximum speed the universe allows, just to cross the thin edge of the galaxy. Within this disk, the Milky Way holds between 200 billion and 400 billion individual stars. The exact number remains uncertain, because our position inside the galaxy makes it difficult to count stars on the far side, where thick clouds of interstellar dust block visible light. Infrared surveys have improved our estimates, but a precise count of every star in the Milky Way is still beyond our current capability. But even the lower estimate is staggering. If you attempted to count every star in our galaxy at a pace of 1 star per second, without pausing to eat, sleep, or rest, the task would take you somewhere between 6,300 and 12,700 years. You would need to begin counting before the construction of the Egyptian pyramids and continue without interruption past the present day and far into the future before you finished. Each of those hundreds of billions of stars is a sun. Some are far larger and more luminous than ours. Blue supergiants like Rigel burn with luminosities exceeding 100,000 times the sun's output. Red hypergiants like UY Scuti have diameters so vast that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt whole. Others are far smaller and dimmer. Red dwarf stars, which make up roughly 70% of all stars in the Milky Way, burn with such feeble luminosity that not a single one is visible to the naked eye from Earth, despite being the most common type of star in the galaxy. Our sun falls somewhere in the middle, brighter than most, dimmer than many, larger than some, smaller than others. In a galaxy of hundreds of billions, our star is profoundly average. And our position within the galaxy is equally unremarkable. The solar system sits approximately 26,000 light-years from the galactic center. We are not near the dense, active core where stars pack together thousands of times more tightly than in our neighborhood. We are not at the sparse outer rim where star density fades to almost nothing. We occupy a position roughly halfway out along the disk, embedded in a minor structure called the Orion Spur, which branches off between 2 of the galaxy's major spiral arms. In galactic terms, we live in the suburbs, quiet, unremarkable, easy to overlook. The sun and everything bound to it orbits the galactic center at approximately 515,000 miles per hour. That sounds fast, and it is. But the galaxy is so enormous that one complete orbit takes roughly 230 million years. This period is sometimes called a galactic year. In the 4.5 billion years since the solar system formed, the Sun has completed only about 19 or 20 full orbits. The last time our star occupied this exact position in the Milky Way, roughly 230 million years ago, dinosaurs were just beginning to appear on Earth. No grass existed, no flowers, no birds. The world was populated by creatures almost unrecognizable to modern eyes. That is one orbit, one lap around the galaxy. And the Sun has done it only about 20 times in its entire existence. Here is a comparison that might help you feel how invisible we are within this structure. If you were standing at the center of the Milky Way and looked outward trying to find our Sun, the task would be equivalent to standing in the middle of a completely darkened Manhattan at night and trying to identify one specific firefly hovering among 400 billion other fireflies scattered across the island. Every firefly is glowing. Every firefly is moving. The one you are looking for is utterly average in brightness, utterly average in size, located in a section of the island with no distinguishing features. You would never find it, not in one lifetime, not in 1,000 lifetimes. Now consider this: every signal humanity has ever broadcast into space, every radio wave, every television transmission, every radar pulse has traveled outward at the speed of light for roughly 120 years since the first radio transmissions in the early 20th century. That means our electromagnetic footprint extends approximately 120 light-years in all directions from Earth. 120 light-years sounds enormous, but the Milky Way is 100,000 light-years across. Our loudest shout into the cosmos has covered approximately 0.1% of our own galaxy's diameter. If the Milky Way were a dining room table, our entire radiosphere would be a small coin lying flat on the surface. To any civilization on the other side of the galaxy, humanity does not exist. Our signals have not arrived. They will not arrive for tens of thousands of years. And when they finally do, they will be so faint, so diluted by distance, that detecting them would require sensitivity far beyond anything we can currently build. See, here is something that scientists continue to debate, and that touches the edge of the genuinely strange. Given the age of our galaxy, roughly 13 billion years, and the number of stars it contains, some researchers argue that if intelligent civilizations arise even rarely, the galaxy should have been colonized many times over by now. This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked the simple question, "And where is everybody?" The galaxy is old enough and large enough that even a civilization expanding at a small fraction of light speed could have spread across the entire disk in a few tens of millions of years. A blink in galactic time. Yet we see no evidence of such expansion. No megastructures. No unmistakable signals. No visitors. Dozens of proposed solutions exist, ranging from the idea that intelligent life is extraordinarily rare to the possibility that advanced civilizations deliberately hide themselves, to the unsettling hypothesis that something consistently destroys civilizations before they can spread. None of these solutions has been confirmed. The silence remains unexplained. The galaxy holds 400 billion stars, and we have heard from none of them. That silence wraps around everything we have measured. A galaxy of staggering size, populated by hundreds of billions of suns, old enough for countless civilizations to have risen and fallen, and as far as we can tell, quiet. But the Milky Way, as vast as it is not the largest thing in our immediate cosmic neighborhood. Something larger lives just beyond the edge of our galaxy's light, and on a clear autumn night, if you know exactly where to look, you can see it with your own eyes. On a clear autumn night in the northern hemisphere, if you look toward the constellation Andromeda, you can find a faint smudge of light. It is dim, slightly fuzzy, easy to mistake for a tiny cloud or a trick your eyes are playing on you. You might glance at it and move on, assuming it is nothing important. Ancient astronomers catalogued it as a nebula, a cloud of glowing gas drifting somewhere inside our own galaxy. For centuries, that is exactly what scientists believed it was. Nobody seriously considered the possibility that this faint smudge could be anything grander than a local patch of luminous gas. The Milky Way was the universe. Everything visible in the sky existed within it. That was the accepted truth, repeated in lecture halls and printed in textbooks without serious challenge. And then one man, one telescope, and one pulsating star changed everything. The story begins in the early 1920s, during a period of fierce scientific disagreement known as the Great Debate. On one side stood astronomers who believed the Milky Way was the entire universe. The spiral-shaped nebulae visible through the telescopes were simply gas clouds within our galaxy. Nothing existed beyond the Milky Way because there was no beyond. On the other side stood a smaller group who suspected something far more radical. They believed these spiral nebulae might be island universes, entire galaxies comparable to our own, located at distances so enormous they lay far outside the Milky Way's borders. Neither side had definitive proof. The debate raged in journal pages and lecture halls, growing more heated with each passing year. The question was not merely academic, it was a question about the size of everything. Either the universe was one galaxy, our galaxy, and nothing more, or the universe was vastly, incomprehensibly larger than anyone had dared to officially declare. The answer came from a mountaintop in Southern California. Edwin Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory. At that time, it was the largest operational telescope on Earth. Its mirror could gather light that smaller instruments could not detect, revealing details in distant objects that had previously appeared as nothing more than blurry smudges. Hubble aimed this enormous eye at the Andromeda Nebula and spent months carefully exposing photographic plates, building up faint light over long hours of observation. What the Hooker telescope revealed was extraordinary. The fuzzy smudge began to break apart. What had looked like a smooth cloud of glowing gas resolved into individual points of light, near stars, not gas, not luminous fog, actual individual stars, each one a sun, embedded within the nebula's glow. Among these newly resolved stars, Hubble found something specific, a Cepheid variable. This is a type of star that pulses in brightness with a regular, predictable rhythm. It brightens, dims, brightens again, over and over, like a cosmic heartbeat. And this particular heartbeat carried information that would shatter the known universe. The key to unlocking that information had been forged years earlier by a woman whose name deserves to be spoken alongside Hubble's, but rarely is. Henrietta Swan Leavitt was an astronomer working at the Harvard College Observatory, where she was employed as a human computer. A woman hired to perform tedious calculations and catalogue photographic plates at a fraction of the salary paid to male researchers. Despite these limitations, Leavitt made one of the most important discoveries in the history of astronomy. By painstakingly studying Cepheid variable stars in the Magellanic Clouds, two small companion galaxies visible from the southern hemisphere, Leavitt established a precise relationship between a Cepheid's pulsation period and its true brightness. A Cepheid that pulsates slowly is genuinely, intrinsically brighter than one that pulsates rapidly. This relationship was consistent and reliable. It worked every time, and it handed astronomers something they had never possessed before, a cosmic measuring tape. Here is how it works. If you observe a Cepheid variable star and measure how long its pulsation cycle takes, you can determine its true brightness using Leavitt's relationship. Then, you compare that true brightness to how bright the star appears from Earth. The difference between how bright it actually is and how bright it looks tells you how far away it must be. The dimmer it appears relative to its true brightness, the farther away it sits. This is the inverse square law of light applied to a star whose true luminosity you already know. It is elegant. It is powerful. And Hubble used it to measure the distance to the Cepheid he had found in Andromeda. He observed the star's pulsation period. He applied Leavitt's relationship to determine its true brightness. He measured how faint it appeared from Earth. He performed the calculation. The result was staggering. The Cepheid, and therefore the nebula containing it, was located approximately 900,000 light-years from Earth. This distance was later revised upward to approximately 2.5 million light-years as measurement techniques improved over subsequent decades. But even the initial estimate was far beyond the known boundaries of the Milky Way. The Andromeda Nebula was not a gas cloud inside our galaxy. It was not a local feature. It was a completely separate galaxy, an entire island of stars lying at a distance so enormous that the light reaching Hubble's photographic plate had been traveling through space for roughly 1 million years before it arrived. In a single calculation, derived from a pulsating star on a glass photographic plate, the known universe expanded from one galaxy to at least two. The great debate was over. The cosmos had just become unimaginably larger than almost anyone had dared to propose. Here is something that adds a strange and poignant layer to this moment. Hubble's groundbreaking observation relied on technology that by today's standards is almost unbelievably primitive. The photographic plates he used were glass sheets coated with light-sensitive emulsion, as each exposure required hours of keeping the telescope pointed at exactly the same spot while the Earth rotated beneath it, demanding constant manual corrections. The data was not digital, it was chemical. Hubble examined the developed plates with a magnifying eyepiece, comparing tiny dots of silver halide, grains to determine which stars had changed brightness between exposures. The discovery that doubled the size of the known universe was made by a man squinting at specks on a piece of glass. And there is an open question that historians of science still discuss. How much credit truly belongs to Hubble, and how much belongs to Leavitt, whose period luminosity relationship made the distance measurement possible in the first place? Leavitt died in 1921, before Hubble published his Andromeda results. She never knew her work had been used to reshape humanity's understanding of the cosmos. Some scholars have argued that Leavitt deserved consideration for a Nobel Prize, but the Nobel Committee does not award prizes posthumously, and her contributions, while foundational, were often overshadowed by the men who applied them. The question of fair credit in scientific discovery remains a living and uncomfortable conversation. But regardless of where the credit ultimately rests, the result stands unchanged. That faint smudge in the autumn sky is not a cloud. It is not a nebula. It is not a feature within our galaxy. It is the Andromeda Galaxy, a structure containing approximately 1 trillion stars, stretched across a disk of space more than 220,000 light-years wide, sitting 2.5 million light-years from your eyes. It is the most distant object visible to the unaided human eye, and it is the single largest thing you will ever see without a telescope. What waits inside that smudge, measured on every axis that science can reach, makes our home galaxy look modest by comparison. And that comparison is where we turn next. That faint smudge you can see with your naked eye on a clear autumn night is not a modest neighbor. It is a giant. And on nearly every axis that astronomers can measure, it dwarfs the place we call home. The Andromeda Galaxy, also known as Messier 31, stretches across approximately 220,000 light-years of space. Our Milky Way spans roughly 100,000 light-years. Place them side by side, and Andromeda would dwarf our galaxy the way a beach ball dwarfs a tennis ball. More than double the diameter means far more than double the area. The visible disk of Andromeda covers roughly 4 to 5 times the surface area of our galaxy's disk. But size is only the beginning. The Milky Way contains somewhere between 200 billion and 400 billion stars, and astronomers remain uncertain about the exact count because our position inside the galaxy makes it difficult to see through the dust clouds that obscure the far side. Andromeda contains approximately 1 trillion stars. Depending on which estimate you use for the Milky Way, Andromeda holds between 2.5 to 5 times as many stars as our entire galaxy. Yet every sun that powers every planet, that harbors every possibility of life within the Milky Way, could be multiplied several times over and still not match the stellar population of the galaxy next door. When you look at that faint smudge in the autumn sky, you are looking at the combined light of 1 trillion nuclear furnaces burning across a disk of space more than twice as wide as everything you have ever known. The differences extend deep into the structures of both galaxies. At the center of the Milky Way sits a supermassive black hole called Sagittarius, a star. It weighs approximately 4 million times the mass of our Sun. 4 million solar masses sounds immense, and it is. A black hole of that size warps space and time in its immediate vicinity, trapping anything that crosses its event horizon, including light itself. Nothing escapes once it falls in, but Andromeda's central black hole makes ours look small. The black hole at the center of Andromeda weighs approximately 100 million solar masses. That is roughly 25 times heavier than Sagittarius A star. If our galaxy's central black hole is a boulder sitting at the heart of the Milky Way, Andromeda's black hole is a small mountain. The gravitational forces it exerts, the volume of space it dominates, the amount of material it has consumed over billions of years, all of it vastly exceeds anything at the core of our home galaxy. This difference tells astronomers something important about each galaxy's history. Supermassive black holes grow by consuming material. Gas falls inward. Smaller black holes merge with larger ones. Satellite galaxies are swallowed, and their central black holes are absorbed. A black hole 25 times more massive than ours suggests that Andromeda has had access to and consumed far more material over cosmic time. It has been a more aggressive eater, a more active cannibal. The evidence for this cannibal history is written across Andromeda's surrounding space. Galaxies do not exist in isolation. Large spiral galaxies like the Milky Way and Andromeda are typically surrounded by swarms of smaller satellite galaxies, by dwarf galaxies containing anywhere from a few million to a few billion stars each. These smaller systems orbit their larger hosts, bound by gravity, slowly circling across hundreds of millions or billions of years. And sometimes they get too close. When a satellite galaxy passes too near its massive host, gravitational tidal forces begin to tear it apart. Stars are stripped from its outer edges. Long streams of stellar debris stretch outward, tracing the orbit like a trail of breadcrumbs left behind by a traveler being slowly devoured. Eventually, over many passes, the satellite galaxy is completely absorbed. Its stars scatter into the halo of the larger galaxy. Its identity disappears. It becomes part of something bigger that consumed it. Andromeda shows unmistakable signs of this process. Two prominent satellite galaxies, designated M32 and M110, orbit nearby. M32 is a compact elliptical galaxy containing roughly 3 billion stars. It passes remarkably close to Andromeda's disk, and observations reveal clear evidence that Andromeda's gravity is actively stripping stars from M32's outer regions. Simulations suggest that M32 may once have been a much larger galaxy, perhaps a medium-sized spiral, that has been progressively dismantled over billions of years of close encounters. What remains is a dense, compact core, the survivor of a slow gravitational murder still in progress. M110 shows similar signs of disturbance. Its outer regions appear diffuse and irregular, stretched by tidal forces from its massive neighbor. Beyond these two visible companions, Andromeda possesses at least 35 confirmed satellite galaxies, and likely more awaiting discovery in deeper surveys. Many of these show evidence of tidal interaction. Streams of stripped stars have been detected arcing through Andromeda's halo, the ghostly remains of galaxies that no longer exist as independent structures. Andromeda is not just larger than the Milky Way, it is a more active gravitational predator, surrounded by the debris of its past meals. Another measure of galactic history comes from globular clusters. These are ancient, dense spherical collections of stars that orbit a galaxy's core. They are among the oldest structures in any galaxy, with many dating back to within 1 billion years of the Big Bang itself. Each globular cluster contains anywhere from tens of thousands to several million stars packed into a volume only a few dozen to a few hundred light-years across. The Milky Way possesses approximately 150 known globular clusters. Andromeda has roughly 450, about 3 times as many. Some estimates push Andromeda's count even higher, toward 500 or more. This richer system of ancient stellar relics speaks to Andromeda's larger gravitational sphere of influence and its more extensive history of satellite absorption. Every consumed dwarf galaxy potentially contributed its own globular clusters to the collection. Here is something genuinely surprising that complicates the simple picture of Andromeda as the dominant galaxy. For decades, astronomers assumed Andromeda was also significantly more massive than the Milky Way in total, not just in stars and black holes, but in the vast invisible halos of dark matter that surround every large galaxy. Dark matter does not emit, absorb, or reflect light. Its presence is detected only through gravitational effects on visible matter. Earlier estimates placed Andromeda's total mass at roughly 1.5 to 2 trillion solar masses, significantly exceeding the Milky Way's estimated mass. But more recent studies, particularly those using data from the European Space Agency's Gaia spacecraft, have revised some of these estimates. A study published in 2018 used the motions of satellite galaxies and globular clusters orbiting Andromeda to recalculate its total mass. The result was surprising: approximately 800 billion solar masses, lower than earlier estimates, potentially comparable to, or even slightly less than, the Milky Way's mass. Other studies have produced different results, with mass estimates ranging from 800 billion to nearly 2 trillion solar masses, depending on methodology and assumptions. The question of which galaxy is truly more massive overall remains an active area of scientific investigation. This uncertainty is itself fascinating. It tells us that measuring the total mass of a galaxy, especially the invisible dark matter that dominates the mass budget, remains one of the most challenging problems in modern astrophysics. Even for Andromeda, close enough to see with the naked eye, we cannot yet agree on how much it weighs. But regardless of where the total mass comparison ultimately settles, the visible differences are dramatic: double the diameter, up to 5 times the stars, a central black hole 25 times heavier, 3 times the ancient globular clusters, a halo littered with the debris of consumed satellite galaxies. The Milky Way is not small. It is a magnificent spiral galaxy containing hundreds of billions of stars spread across 100,000 light-years. But next to Andromeda, it looks like a modest companion rather than an equal partner. And these two galaxies are not sitting quietly at a safe distance from each other. They are bound together by gravity, They belong to the same cosmic family, and right now, at this very moment, the distance between them is shrinking. Something is coming, and it has been coming for a very long time. The Milky Way and Andromeda are separated by approximately 2.5 million light-years of intergalactic space. That distance is so vast that the light reaching your eyes from Andromeda tonight left that galaxy before the genus Homo existed on Earth. It has been traveling through darkness for longer than the entire evolutionary history of human intelligence. And across that entire immense distance, something is happening. Something slow, gravitational, and inevitable. Andromeda is moving toward us. This is not speculation. It is not a theoretical prediction awaiting confirmation. It is an observed, measured, verified fact. The evidence comes from the light itself. When an object moves toward an observer, the wavelengths of light it emits are compressed, shifted toward the blue end of the spectrum. This phenomenon is called blue shift. It is the light equivalent of a siren rising in pitch as an ambulance approaches you. The sound waves compress, the pitch rises. With light, the wavelengths shorten. The color shifts toward blue. Andromeda's light is blue shifted. The galaxy is approaching. This was first measured by astronomer Vesto Slipher in 1912 at Lowell Observatory in Arizona, making Andromeda one of the first galaxies ever observed to have a significant velocity toward our own. The measurement has been confirmed and refined continuously in the century since. Today, using far more precise instruments and techniques, astronomers have pinned down Andromeda's approach velocity with high confidence. The current best estimate places Andromeda's radial approach speed at approximately 110 kilometers per second. Translated into more familiar terms, that is roughly 250,000 miles per hour. At that speed, the distance between the two galaxies shrinks by about 110 kilometers every single second. Over the course of one Earth year, Andromeda moves approximately 3.5 billion kilometers closer, roughly 23 times the distance between Earth and the Sun. Every year, a gap equivalent to almost the span between the Sun and Uranus is erased from the intergalactic void. That sounds fast, and in human terms, it is extraordinarily fast. 250,000 miles per hour exceeds the speed of any machine humanity has ever built. It is fast enough to travel from Earth to the Moon in about 1 hour, but against the scale of intergalactic distance, it is glacially slow. At 110 kilometers per second, closing the full 2.5 million light-year gap to Andromeda would require roughly 4 to 5 billion years. That is approximately the same length of time the Earth has already existed. The solar system formed, cooled, developed life, evolved that life through billions of years of change, and produced the species now reading these words, all in roughly the same span of time that remains before the two galaxies draw close enough to interact directly. Andromeda has been falling toward the Milky Way for billions of years already, and it will continue falling for billions more. But here is where the science becomes more complicated than the simple story usually told. For decades, the standard description of this encounter has been straightforward. The two galaxies are on a collision course. They will slam into each other head-on in approximately 4 to 4.5 billion years. The merger will produce a single massive elliptical galaxy. Yet this story has appeared in countless documentaries, textbooks, and planetarium shows. It is one of the most widely repeated facts in popular astronomy. But the full picture is more nuanced, and scientific understanding has evolved significantly in the last decade. The radial velocity, the speed at which Andromeda approaches us directly along the line connecting the two galaxies, is well established. 110 kilometers per second, had confirmed by multiple independent observations. No serious dispute. However, radial velocity tells you only how fast the gap is closing in a straight line. It does not tell you whether Andromeda is also moving sideways relative to that line. This sideways component, called the transverse velocity, is critical for predicting the exact geometry of the encounter. Will the two galaxies collide head-on? Will they execute a glancing blow, passing close but not directly through each other? Will they miss entirely on the first approach and then spiral back together over subsequent passes? Measuring the transverse velocity of a galaxy 2.5 million light-years away is extraordinarily difficult. The sideways motion translates into a tiny angular shift across the sky, almost beyond the limits of detection. For many years, this component was essentially unmeasured, and most models simply assumed it was small enough that a head-on collision was the most likely outcome. This changed with the European Space Agency's Gaia spacecraft. Gaia was designed to measure the precise positions and motions of stars with unprecedented accuracy. By tracking the average motion of stars within Andromeda relative to extremely distant background objects called quasars, which are so far away they appear essentially motionless, researchers produced the first robust measurements of Andromeda's sideways motion. Studies published in 2019 using Gaia data estimated Andromeda's transverse velocity at approximately 57 kilometers per second, with uncertainties allowing values ranging from roughly 40 to 70 kilometers per second. This is not negligible. A significant sideways component means the two galaxies are not approaching each other in a perfectly straight line. They are on a path that includes a meaningful offset. What does this mean for the eventual encounter? A higher transverse velocity makes a direct head-on collision on the first pass less likely. Instead, the galaxies might perform an initial close flyby, passing near enough for their outer regions to interact gravitationally, but without immediately plunging through each other's cores. After this first pass, gravitational friction and mutual attraction would gradually slow their relative motion, pull them back toward each other, and set up a second approach. This second encounter would likely be closer and slower, leading to more thorough gravitational entanglement. Subsequent passes would follow, each one drawing the galaxies closer, dissipating more energy, until eventually, over a period potentially spanning several billion years after the first close approach, the two systems would coalesce into a single, merged structure. This revised scenario pushes the timeline for a complete merger further into the future. From the commonly cited 4 to 4.5 billion years, some models now suggest the first close encounter might occur around that time, but the final merger might not be complete until 8 to 10 billion years from now. Here is what is not debated by the scientific community. The Milky Way and Andromeda are gravitationally bound. They are approaching. Some form of significant interaction will occur. A merger, eventually, is almost certain over sufficiently long timescales. What remains under active investigation is the precise choreography of the encounter. Head-on impact versus glancing flyby on the first pass, the exact timeline for first close approach, the number of orbital passes before final coalescence, the shape of the eventual merged galaxy. These details depend on measurements that are still being refined, particularly the transverse velocity, the total masses of both dark matter halos, and the complex dynamics of gravitational friction operating across billions of years. The honest scientific position is this: a collision is very likely, a merger is almost certain, but the exact moment-by-moment sequence of events, the precise gravitational dance of 2 trillion star systems approaching across 2.5 million light-years, is still being worked out. Anyone who tells you they know exactly when and how it will happen is oversimplifying. The physics is well understood in principle. The initial conditions are still being measured. But one thing is certain. These two giants are not maintaining a polite distance. They are not drifting apart like most distant galaxies carried by the expansion of the universe. They are falling toward each other, pulled by a gravitational attraction that has been operating since both galaxies formed, and they will eventually meet. What happens when they do is unlike anything your intuition about collisions might suggest. It is slower, stranger, and more beautiful than a simple crash. And it unfolds across timescales that make human civilization look like a single flash of lightning in a storm that lasts for eons. When you hear the word collision, your mind builds a specific picture: objects smashing together, wreckage, debris flying outward, impact craters, explosions, violence compressed into a single dramatic moment. Forget all of that. A galaxy collision is nothing like what your intuition imagines. It is slower than slow. It unfolds across timescales so vast that no living thing could ever perceive it happening. And despite involving trillions of stars, and it is almost entirely gentle. The reason lies in something we measured earlier: emptiness. Stars within galaxies are separated by truly enormous distances relative to their sizes. In the solar neighborhood, the average gap between neighboring stars stretches roughly 4 to 5 light-years. Each star is a few 100,000 to a few million miles across, but the spaces between them span trillions of miles. The ratio of size to separation is almost impossible to visualize. Here is a comparison that might help. Imagine shrinking our sun to the size of a bowling ball. At that scale, the nearest neighboring star would be another bowling ball sitting in a completely different city, hundreds of miles away. The space between them would contain nothing but empty floor. Now imagine 2 clouds of these bowling balls passing through each other, as each cloud contains billions of balls, but the balls are all hundreds of miles apart. The clouds drift through the same region of space simultaneously, and almost nothing touches. The bowling balls slide past each other through all that empty space without contact. A few might come close. An extremely rare pair might actually collide, but the vast majority pass through completely undisturbed. That is what happens when galaxies merge. The stars do not crash into each other. The probability of any 2 stars physically colliding during the entire Milky Way Andromeda encounter is vanishingly small. You could run the simulation billions of times, and direct stellar impacts would remain extraordinarily rare events. But something dramatic does happen, and it happens through gravity. When 2 galaxies pass near or through each other, the gravitational forces involved are immense. These forces operate across scales of thousands of light-years, reaching out across the void between individual stars and pulling on everything simultaneously. They do not need to bring stars into contact to reshape both galaxies profoundly. What gravity does is warp orbits. Every star in the Milky Way currently follows a specific path around the galactic center, a path determined by the combined gravitational pull of all the other matter in the galaxy. See, when Andromeda's trillion stars and massive dark matter halo pass nearby, that gravitational balance is disrupted. Stars that have been following stable orbits for billions of years suddenly feel new forces tugging from unfamiliar directions. Their paths bend, their speeds change. Some are accelerated outward, flung onto long, looping trajectories that carry them far into intergalactic space. Others are pulled inward, are drawn toward the combined gravitational center of the merging system. The elegant spiral structures that characterize both galaxies would be progressively distorted. The graceful curved arms of stars, gas, and dust would stretch, twist, and eventually dissolve into chaotic streams. Over hundreds of millions of years following the first close encounter, the organized disk structures would puff up into rounder, less orderly shapes. The beautiful pinwheel forms would be destroyed. We do not have to imagine what this looks like. We can see it happening right now in other galaxies across the universe. The Antennae galaxies, located roughly 63 million light-years from Earth, are two spiral galaxies currently in the process of colliding. Long streamers of stars extend outward from both systems, stretched into graceful arcs by tidal forces. These streamers resemble the antennae of an insect, which is how the system got its name. At the overlap region, where the two galaxies are passing through each other, enormous bursts of new star formation are occurring, visible as bright knots of young blue stars and glowing clouds of heated gas. The Mice galaxies, another interacting pair, showed two spirals caught at an earlier stage of their encounter. Each galaxy trails a long tail of tidally stripped stars extending hundreds of thousands of light-years into space, like ribbons pulled behind dancers spinning past each other. The Cartwheel galaxy captures something even more violent. A smaller galaxy appears to have punched directly through the center of a larger spiral disk, sending a shockwave of compressed gas radiating outward in an expanding ring. New stars ignite along this ring like a ripple of fire spreading across a pond. The smaller galaxy passed completely through and is still visible nearby, leaving behind a bullseye structure unlike anything in our local cosmic neighborhood. These systems are not simulations. They are real galaxies observed at various stages of gravitational interaction, providing a visual catalogue of what the Milky Way Andromeda encounter will resemble across different phases separated by hundreds of millions of years. But stars are only half the story. The gas within both galaxies responds very differently. Stars are compact objects separated by vast distances. They pass through each other's galactic space without direct interaction. Gas clouds, however, are extended and diffuse. When the interstellar gas from two galaxies meets during a merger, it collides, compresses, and heats up dramatically. This compression triggers enormous waves of new star formation. Regions that had been quiet for billions of years suddenly ignite with the birth of millions of new stars. The collision essentially squeezes the raw material of star formation together, accelerating a process that would otherwise take far longer. The merging system lights up in infrared and ultraviolet radiation as these starburst regions blaze across both galaxies. Astronomers observe this phenomenon in colliding galaxy pairs throughout the universe. The starburst phase is one of the most distinctive signatures of a galactic merger in progress, but this phase is temporary. The violent compression exhausts available fuel relatively quickly in cosmic terms. Within a few 100 million years, the easily accessible gas is either converted into new stars, heated to temperatures too high for gravitational collapse, or expelled entirely from the merger region by the energy output of the newly formed stars and any active galactic nuclei triggered by material falling toward the central black holes. After the starburst subsides, star formation declines sharply. The merged galaxy begins to quiet down. The end state, it reached perhaps 1 to 2 billion years after final coalescence, would be a massive elliptical galaxy. No spiral arms, no organized disk, just a roughly spherical or slightly elongated blob of stars orbiting a common center of mass in randomized directions. The elegant spiral structures of both parent galaxies would be gone forever, replaced by a smooth, featureless glow of ancient stars slowly aging together. Astronomers have proposed several names for this future merged galaxy: Milkomeda, Milkdromeda. The names are playful, but the structure they describe would be immense. A combined system containing somewhere between 1.5 and 2 trillion stars, with a total mass potentially exceeding 2 trillion solar masses. Here is something strange and still being studied. At the center of this merged galaxy, your 2 supermassive black holes would initially orbit each other. The 4 million solar mass black hole from the Milky Way and the 100 million solar mass black hole from Andromeda would spiral slowly inward over millions of years, radiating gravitational energy as they go. Eventually, they would merge in a cataclysmic event that would produce gravitational waves, ripples in the fabric of space-time itself, powerful enough in principle to be detected across the observable universe. The final merger of 2 supermassive black holes is one of the most energetic events the universe can produce. For a brief moment, the energy output in gravitational waves would exceed the combined light output of every star in both galaxies. And then it would be over. A single, larger black hole would sit at the center of the new elliptical galaxy, and the merger would be complete. From any planet orbiting any star caught in this merger, the changes would be imperceptible on human timescales. Galactic mergers unfold across hundreds of millions of years. The night sky would shift gradually across millennia, not suddenly in a lifetime. A watcher would see unfamiliar stars slowly appear, constellations slowly distort, the band of the Milky Way slowly warp and dissolve, but no individual would ever perceive a sudden change. It would be like watching a mountain erode, real, powerful, transformative, but invisible to any single pair of eyes that tried to see it move. Everything we have measured so far, every distance that made your mind stretch, every comparison that forced you to rebuild your sense of what counts as large, has led us to this question. The question that matters most to any creature that looks up at the night sky and wonders, could we ever go there? Could any spacecraft, any technology, any civilization confined to the Milky Way ever cross the 2.5 million light-year gulf to Andromeda? Could biological beings ever make that journey within any time frame that means something to the beings attempting it? The answer comes not from pessimism, it comes from arithmetic, and the arithmetic is devastating. Let us start with what humanity has actually built. The fastest object we have ever sent into deep space on an outbound trajectory is Voyager 1. It travels at approximately 38,000 miles per hour relative to the Sun. That is faster than any car, any airplane, any bullet, any rocket that has ever carried a human being. It represents genuine engineering achievement, decades of work by thousands of people, the best propulsion technology available when it launched in 1977. At that speed, traveling continuously, without slowing, without interruption, without encountering any obstacle, Voyager 1 would require approximately 44 billion years to reach Andromeda. Let that number settle. 44 billion years. The current age of the universe, measured from the Big Bang to this moment, is approximately 13.8 billion years. The journey to Andromeda at Voyager speed would take more than 3 times the entire age of the universe. If Voyager had been launched at the moment of the Big Bang itself, before galaxies or stars or planets existed, it would still not have arrived at Andromeda by now. It would still have roughly 30 billion years of travel remaining. The fastest machine our species has ever created cannot reach the galaxy next door in any time frame that the universe itself has yet provided. What about faster spacecraft? What about the Parker Solar Probe, currently the fastest human-made object relative to the Sun, reaching speeds of approximately 430,000 miles per hour during its closest solar approaches? At that speed, reaching Andromeda would still take approximately 3.9 billion years. The Earth is 4.5 billion years old. Complex multicellular life has existed for roughly 600 million years. the fastest object humanity has ever built would need a travel time roughly equivalent to the entire current age of our planet to reach the nearest giant galaxy. What about theoretical technologies? What about spacecraft that do not yet exist but are grounded in real physics? The Breakthrough Starshot initiative proposed using powerful ground-based lasers to accelerate tiny, lightweight probes to approximately 20% of the speed of light. At that velocity, such a probe could reach the nearest star, Proxima Centauri, in roughly 20 years. It is an ambitious concept, and even if the immense engineering challenges were eventually solved, the technology would be designed for interstellar distances measured in single-digit light-years, not intergalactic distances measured in millions. But let us be generous. Let us imagine a civilization far more advanced than ours, one that somehow builds a spacecraft capable of traveling at 10% of the speed of light. This is not a minor assumption. 10% of light speed is approximately 67 million miles per hour, nearly 2,000 times faster than Voyager. Achieving this velocity with any meaningful payload would require energy outputs so far beyond current capability that no serious engineering roadmap exists for producing them. But grant the assumption. At 10% of light speed, the journey to Andromeda would take 25 million years. 25 million years ago on Earth, the ancestors of modern great apes had not yet separated from the ancestors of old-world monkeys. The Himalayas were still being actively pushed upward by tectonic forces. The entire evolutionary lineage that produced modern humans could fit inside this travel time, with room to spare. A spacecraft departing at 10% of light speed when early primates were swinging through Oligocene forests would arrive at Andromeda roughly now. The passengers would need to sustain not just themselves, but an entire functioning society, a closed ecosystem, a stable technological infrastructure, and a coherent sense of purpose across a span of time longer than most mammalian species survive on Earth. Push the speed higher. Imagine 50% of light speed. At that velocity, the journey takes 5 million years, still longer than the entire existence of the genus Homo, still requiring a generation ship that somehow maintains continuity across approximately 200,000 human generations. Here is something that touches the boundary of known physics and remains an area of active theoretical speculation. Some physicists have explored concepts that might, in principle, allow faster-than-light travel. The most famous is the Alcubierre drive, a theoretical construct proposed in 1994 by physicist Miguel Alcubierre. It describes a bubble of warped space-time that contracts space in front of a spacecraft and expands it behind, allowing the bubble to move faster than light, while everything inside it remains stationary relative to local space-time. The mathematics is valid within the framework of general relativity. The physics does not violate the rule that nothing can travel faster than light through space because the spacecraft is not moving through space in the conventional sense. Instead, space itself is being manipulated around it. But the practical requirements are almost certainly impossible. The original formulation required negative energy, a form of energy that may not exist in usable quantities anywhere in the universe. Subsequent refinements reduced the energy requirements, but still demand exotic matter with properties no experiment has ever produced or detected. The Alcubierre drive remains a mathematical curiosity rather than a realistic engineering target. Most physicists consider it permanently beyond reach. Without faster-than-light travel, the barrier is absolute. Even at 99% of light speed, where relativistic time dilation becomes significant, the external journey time remains approximately 2.5 million years. The universe outside the ship ages by that amount, no matter how fast you travel. But time dilation can compress the subjective experience for passengers inside the spacecraft. At constant 1g acceleration, which would conveniently provide Earth-like artificial gravity, the onboard experience might be reduced to roughly 28 years. But this scenario hides problems so severe they border on fantasy. Maintaining 1g acceleration for a 2.5 million light-year journey would require energy expenditure exceeding the total output of the Sun across significant fractions of its lifetime. No known or theorized fuel source could provide it. No engineering, even remotely within our current understanding, could build such a propulsion system. And the travelers who arrived after 28 subjective years would step out into a universe that had aged by 2.5 million years. Everyone they knew would be gone, not dead for a few generations, gone for 2.5 million years. Their home galaxy would be unrecognizable. The civilization they departed from would have risen, fallen, and been forgotten long before they arrived at their destination. This is not exile. It is erasure from history. And there is another problem rarely discussed in popular accounts. The Andromeda they aimed for would no longer exist in the form they studied before departure. Over 2.5 million years, massive stars would have exploded as supernovae. New stars would have formed in regions that were empty gas clouds when the mission launched. Stellar positions would have shifted. The spiral arms would have rotated into different configurations. The travelers would arrive at a galaxy that had aged beyond the recognition of their charts and instruments. The distance to Andromeda is not merely a large number. It is a physical boundary, not a wall made of matter, but something more fundamental. A boundary imposed by the geometry of space, the speed of light, the energy requirements of acceleration, and the biological limitations of every known form of life. Within the framework of known physics, intergalactic travel is not a difficult engineering problem awaiting a clever solution. It is a barrier as real as the laws of thermodynamics, as absolute as the speed of light itself. And yet, there is something waiting for us beyond this devastation, something that reframes everything we have just measured. We have traveled a long way together through these measurements. We started on a planet that felt enormous, a world that took our ancestors 10,000 years to walk partway across. We watched that planet shrink into a smooth marble the moment we lifted our perspective by just one level. We felt the Mariana Trench, the deepest wound on Earth's surface, vanish into imperceptibility on a basketball-sized globe. We measured 93 million miles to our own star and discovered a thermonuclear furnace so massive it could swallow the Earth 1.3 million times over. We wandered through the emptiness of the solar system, where Voyager whispers across 15 billion miles with the power of a refrigerator bulb. We crossed the interstellar desert to the nearest neighboring sun and found a 73,000-year journey waiting at our fastest current speed. We stood inside the Milky Way and counted 400 billion stars spread across 100,000 light-years. We learned that every radio signal humanity has ever broadcast covers less than 0.1% of our own galaxy's width. We are invisible even within our home. We looked toward Andromeda and saw 1 trillion suns burning across a disk, 220,000 light-years wide. We learned it is falling toward us at 250,000 miles per hour, closing a gap 2.5 million light-years deep. We watched what a galactic merger looks like, not a collision of crashing stars, but a slow, gravitational dance spanning billions of years, dissolving spiral arms, igniting starbursts, eventually producing a single elliptical giant. And then we did the arithmetic on crossing that distance. We found that even our fastest spacecraft would need 44 billion years to make the journey. We found that even at 10% of light speed, the trip would take 25 million years. We discovered that the gap between galaxies is not merely large, but represents something closer to a permanent boundary for biological life. Everything we measured told the same story. You are small, you are confined. The distances are too vast. The timescales are too long. The energy requirements are too extreme. The universe was not built for biological creatures to travel between its largest structures. And all of that is true, but it is not the whole truth. Here is the part that gets lost in the overwhelming scale of cosmic distance. Here is the thing that deserves your attention as much as any measurement we have made tonight. You saw Andromeda, not through a telescope, not through a space probe, not through any instrument more sophisticated than the soft, wet tissue at the back of your eyes. On a clear autumn night, you can walk outside, look towards the constellation Andromeda, and see the combined light of 1 trillion stars burning 2.5 million light-years away. Photons that left that galaxy before your species existed, traveling through the intergalactic void for longer than the entire history of human evolution, end their journey on the surface of your retina. They are absorbed by cells called rods and cones, converted into electrical signals, transmitted through your optic nerve, and processed by a brain weighing roughly 3 pounds, running on approximately 20 watts of power. That brain, that small biological organ consuming less energy than a dim light bulb, has done something remarkable. It has measured what it cannot touch. It has calculated distances it cannot cross. It has mapped structures so vast that no journey within known physics could ever traverse them. You cannot go to Andromeda. Almost certainly, no biological creature from the Milky Way ever will. The distance is too extreme. The energy requirements are too immense. The timescales exceed the survival span of species, civilizations, and possibly even stable technological societies. But you know Andromeda exists. You know its diameter, its star count, its central black hole mass, its approach velocity, its transverse motion, its satellite galaxies, its globular cluster population, its merger history. You know more about a structure 2.5 million light-years away than your great-grandparents knew about the next continent over. This is not nothing. This is extraordinary. The universe has no obligation to be comprehensible. There is no physical law requiring that the cosmos be measurable by the creatures living inside it. The same physics that creates distances too vast to cross also creates brains too small to understand, in almost every other case we might imagine. A bacterium cannot comprehend the ocean it floats in. An ant cannot map the continent it walks across. Most living things exist entirely within their immediate sensory environment and are aware of nothing beyond the reach of their bodies. But somehow, on a small rocky planet orbiting an average star in the quiet suburbs of an ordinary spiral galaxy, something different happened. A species evolved that could look at a smudge of light in the night sky and determine it was another galaxy. A species that could measure the distance to that galaxy using pulsating stars and mathematical relationships, discovered by a woman paid a fraction of what her male colleagues earned. A species that could calculate the velocity of approach, model the eventual merger, predict the birth of a new elliptical galaxy billions of years in the future. The scale is terrifying. The distances are permanent. The isolation is real. But so is the measurement. And there is something in that fact, something quiet and precise and irreducible that deserves recognition. Here is something that might offer a strange form of comfort. The very atoms in your body were forged inside ancient stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was cooked in stellar furnaces and scattered across space by supernova explosions long before Earth existed. You are made of star material. The universe built you out of itself. And now, that same universe has produced an arrangement of atoms capable of looking back at the process that created it, and understanding, at least partially, how it all works. You are the cosmos measuring itself, the universe examining its own structure through eyes that it assembled from its own debris. That is not a small thing. That is perhaps the most remarkable thing that has ever happened in 2.5 million light-years of space. Let your breathing slow now. Let the numbers we measured together settle into the quieter parts of your mind, not as burdens, but as landmarks in a territory you have glimpsed and will continue to explore in your own way. The Earth still holds you. Its gravity still keeps your body pressed gently against its surface. The air still fills your lungs with each slow breath. The night sky still waits outside your window, carrying the light of 400 billion local stars, and just beyond them, the faint ancient glow of 1 trillion more. You are small. That much is certain. You are confined to one galaxy among trillions, rooted to one planet among billions, alive for one brief moment in a cosmic timeline that stretches billions of years in either direction. But you are also aware. You are conscious. You can measure distances you cannot cross, map structures you cannot touch, understand processes that will not complete until long after your species has vanished. And tonight, that awareness has carried you across 2.5 million light-years of space and back again without leaving your room. The giant next door will continue falling toward us. The merger will happen, or something like it, in 4 or 5 or 10 billion years. The spiral arms will dissolve. New stars will be born in the collision. The black holes will eventually combine in an event that ripples across space-time itself. None of that is your burden to carry. It will unfold on its own schedule, indifferent to human concern. Your task is simpler. Breathe. Rest. Let the scale of the cosmos settle around you like a blanket rather than a weight. You have seen far tonight. You have measured distances that would break most minds that tried to hold them. Now, let them go. Let your eyes close. Let the darkness behind your eyelids feel safe, familiar, and small in the best possible way. The universe will still be there tomorrow. Its distances will still be vast. Its structures will still be immense. And you will still be here, small and aware, capable of looking up and knowing what you see. That is enough. That has always been enough. Rest now. The stars will keep burning without your attention. The galaxies will keep drifting on their ancient paths. And you, made of the same atoms as all of it, can simply be still. Sleep well. You have traveled far.